In this video, we will have a look at a more advanced recursion problem. And to solve this problem, we'll make use of backtracking, which is a concept that often occurs in the context of recursion. And to illustrate all that, we'll play the n-queens puzzle. And the goal of the n-queens puzzle is to place n queens on a n by n field. And the queens have to be placed in such a way that they cannot attack each other. So we can start, for example, by placing here in the top left one queen. And then it already shows us in blue here which fields are now forbidden, because if we would place a queen here, then these two queens could attack each other. And so the first available option is then in the second row in this field here. And now we can already see that in the third row we cannot place a queen. So we have to skip to the fourth row and we don't end up with a solution. And so what we do is we backtrack. So we go back on our track by undoing the steps that we did. And we undo our steps until we can take another path. So by undoing this queen placement, we cannot take any other steps. So we have to go back further, also removing this queen. And now we have the option to place our queen here, for example. Then we get the option to place it here, which again doesn't yield a solution. So we undo that step, we try here, also doesn't work, we go back. So also removing that queen. Then we try here, which actually gives us the same state that we had before. So that is also not working. We try here, also not working. We try here, also not working. And finally here, and that is also not working. And so we've explored every path that arose from placing our queen in this first spot here. And so since everything ends up in a dead end, we also undo this step. And then we place our queen here. Now we have the option to place here, and then here. And there we have it, a solution to our n-queens problem. We can also illustrate this backtracking by looking at a search tree. And when we're doing backtracking, we're doing depth first search. So we go deeper, deeper, and deeper. And when we end up in a dead end, we go back on our track, so we backtrack and then take another option. So we go into here. If that also isn't a solution, we go back again. And then since everything is explored from this node on, we go back again, go in here, back here, and then so on. Now, before we jump into coding the n-queens problem, let's talk first about how we can solve this recursively. Because from what you've seen, you might think that we just iteratively place a queen in every row. So first row, second, third, fourth, and so on. And that's of course one approach that could work, but we can also formulate our approach recursively. And for this recursive formulation, we will have a solve function. And this solve function will get the board state and also a row where it has to place a queen. So we can imagine it gets row 1, so it places a queen in here, and then inside of the solve function we recursively call solve again, now with row plus 1. So first the row was 1, now we solve for row 2. So then inside of the solve function, the solve is called again, now for this row, and so maybe we place the queen in here. And then this recursion continues until all the rows are filled with queens. Okay, so let's start coding this. And to represent our board, we'll use NumPy. And from NumPy we take the np.zeros, so without any queens, our board is just zeros. And we'll also choose a board size, let's say n equals 4. So then the shape to the np.zeros is n, n. And we can also print the board to check that everything's alright. And that looks good. And now before we jump into the solve function, we will first write the function that checks if a placement of a queen is valid. So let's call that function valid. And this function gets the board and also the row and column that we want to place our queen in. And the first thing that we can check is if there are any queens in the row or column that we want to place our new queen. So we check if 1, so we will represent our queens as 1s. And we check if a queen, so a 1, is in board. And then first we specify the row, and we want the whole row. So we use the colon to indicate we're not interested in a specific column. So that covers queens in the same row. And then we also want to cover queens in the same column. So we check if 1 in board, and now all of 1 column. And if that's the case, then we would return false. Now we also have to check the diagonals. So let's say we want to place our queen here. Then we have to check that there are no other queens in this diagonal and this diagonal. And maybe it's best to illustrate that with a different array. So let's initialize the array A with a range, and we go from 0 to 16, and we reshape into 4 by 4. And now NumPy provides the function diagonal, so we can call on our array a.diagonal, and that gives us then the standard diagonal, so these values here. But of course sometimes we want to read these diagonals or even the ones going in the other direction. But let's first take care of the normal direction. And so what we can pass the diagonal functions is a offset. So we can write, for example, 1, and then we get not this diagonal, but the diagonal that is offset by 1. So the 1, 6, 11 here. The same works for minus values. So now we get this diagonal, which is shifted 1 to the left. And so how do we know which diagonal we want? So let's imagine we place our queen in the second row and also in the second column. So in this case, on this 10 here, we would place our queen. And for that, the diagonal has no offset. So essentially, we're starting the diagonal from here, so the index 0, and then get these values here. So let's write the 0 here, and that gives us that. Now let's place the queen in the third column. So we're again second row, but now third column. And now our diagonal, if we trace it back, has a offset of 1. And you might already see where this is going, because when we go back, we go 1 to the left for each row. So we're in the second row, we start in the third column, and we go to the left 2 times. So 1 and 2, 1 for each row. And so we can express the start of our diagonal by writing column minus row. So let's think that through for another scenario. So let's say we have row 3 and column 1. So now we are in here, and in this case we would go back 3 times. So for every row, first here, then here, and then here. So we went 2 times outside of this bracket, which would leave us at the index -2. And so if we run that, we can see we get the appropriate diagonal. So here we are placing our queen, and it checks this diagonal, so the 8 and 13. Okay, so let's add that to the valid function. If there's a 1 in the board diagonal, with the offset column minus row, then we also return false. Okay, so now the flipped diagonal, so this direction. And because there is no real diagonal function that covers this direction, we can just flip our board. So we can write np.flip, and we flip from left to right. That wraps around our array, and then on this we can again call the diagonal function. So maybe let's also print the flipped board. And so let's start with the normal case again. Let's say row and column are equal, so both are 2. So we are placing a queen in here, and now we're interested in this diagonal, so 13, 10, 7. And if we flip our board, we're now interested in this diagonal, so again 7, 10, 13. And this brings us to the same problem that we had before. So we have a queen somewhere, and we want the diagonal. So essentially we're calculating the offset again. The only difference is that our queen changed the column due to the flip that we applied. So originally our queen was here in column 2, but now it's in column 1. And so instead of writing column minus row, we have to change the column value according to the flip. And so let's play through for some other values. If our queen is in here, so in the last column, then it will be in the first column. If we're in the first column, then we're now in the last column. And what this all equals to is saying n minus column, where n is the number of columns that we have. And we also have to add a -1 because we're dealing with indices. And let's also add some brackets to that. So if we start in here, so the column is 3, then we have 4 minus 1, giving us 3, and then 3 minus 3 is 0, and so we get to the beginning here. If we start in here, so column being 0, then we have 4 minus 1 is 3, and 3 minus 0 is 3, and so we end up in here. Okay, so that's the new column, and then we again subtract the row, because we're taking steps back, and that brings us to the appropriate offset. Okay, so let's take that piece of code and write another condition. If our 1 is also in that diagonal, and we replace the a with board, then we also return false. Okay, so now let's actually solve the n-queens problem. So we write the solve function, and the solve function, as previously mentioned, takes the board and also the row where we want to place the queen. Okay, so now let's say we're in some row, let's say maybe the first row here, and then we want to check where we can place our queen. So we iterate through this row to check where placement is possible. Of course, here we can place it already in the first slot, but imagine we're in the second row, then we skip the first 2 and then place it in here. So we write for column in range n. So we write column because essentially we're going through the columns, so first column, second column, third column, but all happening in the row. And so for every tile in this row, we check if the placement is possible. So we call the valid function and check if it's valid for the current board state, the row that we're in, and the current column of our for loop step. And if it's possible, then we place our queen. And so we index our board with our row and column, and we place a 1, representing our queen. Okay, so now we have taken care of one row, but of course there might be still some rows left. And so what we do is we simply call the solve function again, passing again the board, but now also the row, but the next row. So we write row plus 1. And so with this call, we end up again here. And now we can take care of the case where we finished all the rows. So let's say row equals n. And this doesn't have to be n minus 1, because if n equals 3, then that is the last row, and then solve is called again, now with 4, which is of course not a valid index, but it corresponds to the length of our board and also width. And so if that equals then the row, then we can return true, because this can only happen if we successfully place the queen in every row. And so we return true. Okay, so we remember that we called this solve function here again, we ended up in here, and we tackled this case. So what if our row was first 3, so then 3 plus 1, 4, and we then return this true here? Then this true has to be caught somewhere. Or let's ask another question. What should happen if solve returns true in here? So if solve returns true in here, that definitely means that we're done solving our board. So if the board is solved, then we should definitely return. And we can also give a value to this return, namely true, since we did solve the board. And so now it depends on which level of recursion we are. So if we've recursively called solve very often, then this true is returned to here, then the if triggers again, we return again true, and so on and so on. And eventually the true is returned to our main code here, so some solve call in here. Okay, but what happens if our board is not solved? So let's say the solve returns false. Or maybe let's ask first, when can solve return false? Because right now we're only returning true. And so false should be returned when we end up in a dead end. So let's say we place here, here, and then in this row, we will iterate through all the columns, but we cannot place a queen anywhere. And so in this case, the board is not solvable and we should return false. So in our code, after going through all the columns and not finding any spot to place our queen, we know that our board is not solvable. So once the for loop has finished, we can definitely return false, because there was no available spot for our queen. And so this false can then end up here, triggering our else. And at this point we know that this placement of our queen led to a dead end. We call our solve on an empty board, we iterate through our columns, and we check if a placement is valid. So for example, this placement here is valid, so we place our queen, we set the row and column to 1, and then solve is called again, now in row plus 1. So we are in here, we check which spot is valid, this is not, this is not, this is, so we place our queen in here. Then solve is called again, we again go into this loop, but now in this row there is no possible placement, so we finish our loop and then return false. And so this solve call is then finished, and then what we should do is that we undo this queen placement, because apparently it led us to a dead end, so we backtrack. And in our code this just means that we change the board from a 1 again to a 0. And then after we place a 0, we again continue in a previous for loop. So now instead of placing here, we would place here and then continue the whole thing. And this also didn't work, so this will return false, triggering the removal of that here. And also here the for loop finished, so we're in the last place, but we didn't return true because the board is not solved, so that is removed. And now we're taking the next step here. And then again, solve is called and so on. Okay, so let's actually run our code. So we have our board up here and we can call the solve with our board. And also we pass it a starting row and we start in row 0. And if we run our code, it doesn't show us anything because we first have to add a print. And it actually tells us false, so that our board is not solvable, but that is just because we missed a return true in here. So we covered the cases where there is a queen that can attack another queen, but if that's not the case, then we of course have to return true. And now our board is solvable, and we can also print our board. And we see that's the same pattern that we saw in our game here. We can also check for a higher n, so let's say n equals 5, and that also looks good. We can also check n10, and that also looks like a valid solution.